All right, welcome everyone to this month's Journal Club. We will be talking about a paper, measurement of the alpha particle monopole transition form factor, challenges theory, a low energy puzzle. Let me just say a few words about myself and about the Journal Club. My name is Kevin Dustling. I'm an editor for Physical Review Letters. I handle papers in nuclear physics, particle physics, astronomy, and astrophysics. And this particular paper was one that I handled back in June, and that will be the focus of today's discussion. Just to say a few words, Physical Review Letters wants to be a welcoming home to all of the best physics across the entire physics community. The Journal Club is one way to bring people together from different communities to discuss different results. But we want to continue publishing some of the best papers. And I just want to point to you that for the past 13 years, Nobel Prize winning research has been published and cited as critical papers in the Nobel Prize announcements. So this infographic on the left shows some of the results from going back to 2011 all the way up to 2022. And I'm proud to say that we have more work to do, as this infographic needs to be updated, because there were 5 PRLs and 1 PRA that was cited in the 2023 Nobel Prize announcement on attoscience. So this will have to be updated. One more announcement before we get to the matter at hand is I'd like to point you to a recent collection that was just recently put together by a handful of editors that work on these topics at Physical Review. It's a collection to celebrate the 50th anniversary of asymptotic freedom and quantum chromodynamics. So you could find this on our journal homepage, a link to it, and it's just a collection of papers, both some new and some old, that sort of spans the entire history, the 50-year history of how QCD was developed. So finally, I'd like to get to the paper at hand. Again, this was published back in April of 2023. The title of the paper was Measurement of the Alpha Particle Monopole Transition Form Factor Challenges Theory, a Low Energy Puzzle for Nuclear Physics. This was a paper that was highlighted as an editor's suggestion, and it was written about in a physics magazine Viewpoint. It also received lots of coverage, for example, in Physics Today magazine, as well as Quantum magazine. And so that will be the paper that will be discussed today. Moderating discussion is Dean Lee, who is currently at Michigan State. And let me say a few words about Dean. So Dean Lee received his PhD in physics from Harvard University in 1998. He was a postdoc at the University of Massachusetts Amherst from 1998 to 2001. And in 2001, he joined North Carolina State University as an assistant professor in 2001, moving to associate in 2007, and a full professor in 2012. And actually after that, I was actually at North Carolina State, and it was a pleasure to work there as a postdoc, and Dean and I chatted quite a bit about lots of different physics. But then in 2017, he moved to the facility for rare isotope beams at Michigan State University, and he is currently the theoretical nuclear science head at EFRIT. So I'll now pass the floor over to Dean, who will introduce our speakers.
Thank you very much, Kevin. I will indeed introduce the speakers. Before I do that, I will just give a little bit of an introduction for those who may not be in nuclear physics and not already versed in the topics. So this paper is about the helium-4 nucleus, which is also known as an alpha particle. It is composed of 2 protons and 2 neutrons. The ground state has a binding energy of 28.29 MeV, mega electron volts. It has a spin 0 equal to 0. And positive parity, and so we call it a 0+ state. It has been well studied, and its properties are well described by ab initio, or first principles calculations. The first excited state of helium-4 is also a 0+ state, but it is quite different from the ground state. It has an energy that is 20.21 MeV higher than the ground state, which is quite fairly high above. It is an unstable resonance that sits about 400 kiloelectron volts above the threshold for decay into a proton and hydrogen-3, or also known as a triton. In order to study the properties of the second 0+ state of helium-4, experimentalists can use things like inelastic electron scattering on the ground state of helium-4. This scattering excites the second 0+ state, and a momentum-dependent amplitude known as the transition form factor from the ground state to the excited state can be determined. Earlier measurements of the transition form factor disagreed with theoretical calculations. However, the experimental uncertainties were too large to draw definitive conclusions. Now, the A1 collaboration at the Mainz Microtron, or MAMI, has performed this measurement with much smaller uncertainties and confirms the discrepancy. The story of this exciting new measurement and the implications for ab initio nuclear forces and nuclear structure calculations will be the topic of this PRL journal discussion. And our presenters today are authors on this paper. They are Constantina Safienti and Sonia Baca. I will now give you the bios for each of the presenters. Constantina Safienti received her PhD in 2000 from the University of Catania. She was an Alexander von Humboldt Fellow at GSI in 2001 and postdoc there until 2008. From 2008 to 2010, she was assistant professor at the University of Catania, and since 2010, she is full professor at Johannes Gutenberg University in Mainz. Sonia Baca received her PhD in 2005 with an exchange cooperation between the University of Trento and Johannes Gutenberg University in Mainz. She was a postdoctoral researcher at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt from 2005 to 2008, and at Triumph in Vancouver from 2008 to 2009. She worked as a staff scientist at Triumph from 2009 to 2017, holding an adjunct professorship at the University of Manitoba and a position at the University of British Columbia. In 2017, she joined Johannes Gutenberg University in Mainz as a professor of theoretical nuclear physics, and her main research interests are in electroweak reactions for few and many body systems. So if you have any questions, go ahead, type them into chat or raise your hand, and you can then present the question in person with your video and audio. But we will not take questions during the presentations. And at this time, we'll start off with our first presentation by Constantina.
So thank you very much, Dean. Now it will be tough to top your introduction, right? And say something in addition. So thank you very much for giving us the opportunity to talk about our research at this Physics Journal Club. The research I'm going to present is entirely based on the PhD thesis of Simon Kegel, whom you see here. He cannot join us today because after his PhD, he moved from academia to industry. And it is also the work of an entire collaboration. As you have heard, the A1 collaboration, we are based in Mainz. And Mainz is a city known for very nice landscape. It sits on the Rhine River, excellent wine. And we like to think also for the Mainz Microtron, which is our electron accelerator in the field of electromagnetic probes. MAMI is very well known for its high intensity, resolution, and polarization. And last but not least, that for experimentalists is a pretty important point, is the reliability. Here you see a floor plan of the 3 stages of the accelerator, and then the beam is sent to the A1 hole, where the 3 spectrometers sit. With this experimental setup, we can measure the scattering angle and the momentum of the scattered electrons with very high precision. And here you see, I don't know if you remember, that's a typical unit of measure now for height, the Bernie mitten in our A10. So we can send up this beam on different targets, and among all the targets we have used so far, helium stands out because it's one of the lightest stable systems, and therefore it can be used to actually test modern nuclear forces and few-body method. It has also, as you have heard, a very nice 0+ resonance sitting at about 20 MeV, so that's by the time you measure the scattered electrons with our setup, you can reconstruct the missing mass of helium. And here you see the very nice resonance at 20 MeV. So what you do you measure, you measure the transition form factor that describes the whole dynamics between the ground state and the first excited state. How you do that? Well, you just simply count the number of events. Here is a zoom underneath these resonance. You have the cross-section, and the cross-section gives you the transition form factors. The challenge lies in the fact that this resonance is sitting on the top of a huge background. So if you don't have the right setup with high resolution, then it's a problem. And that explains that's the status before our measurement, why data were pretty scarce. Here is now, as a function of Q squared, these transition form factors, large error bars, unknown normalization. And then it happens that when theory compares with such data quality and it doesn't fit, fingers are pointed at the experimentalist. So, and that's the reason why we decided to come to the rescue of the group. And that's the Q squared range which we can cover with our A1 setup, and we performed this new experiment. Now, actually, it is a bit of cheating saying you just simply count the number of events underneath this peak. The analysis is a bit more complicated because the cross-section depends on many different factors. Now, some of them are, let me say, straightforward. Simon would kill me because it needed a lot of time to determine them rather precisely. But for example, the integrated luminosity, you can monitor that over the whole beam time. Detector efficiencies, these you can calibrate them extremely precisely, and the same applies to the phase space. The big effort goes in the determination of the background and the real number of counts underneath the resonance. So what is this background? Here you see again the same plot which I've shown you at the beginning. You have two different kinds of background. One is purely experimental. Helium is a gas, so you need to hold it, and therefore you normally have an aluminum wall which is enclosing the cryogenic helium, and you see it here, the contribution in red. And then on the other side, this you can actually measure. You do what we call empty target run, so you decrease the pressure of helium, and what remains is mostly aluminum. You can measure and you can tune your simulation so that you can reproduce it really nicely. The second background is the physical background, and that is the long radiative tail of the elastic scattering on the ground state of helium. And on the top of that sits the resonance. That you can also simulate, and here you see how painful that can get. So in red are the empty target runs, so are the empty target data. And then you see in pink, you barely see it because it just sits nicely on the top of the data, is the combined simulation. So what you put in the simulation is the whole simulation of elastic, inelastic electron scattering on aluminum. And you can very nicely see all the different resonances of the aluminum. You have the quasi-elastic of aluminum, and here you see the tail of the scattering on helium. Then you combine them all, and they lie on the top of the other, and so you can subtract that. And then you subtract that. If I learn how to move under zoom, will be better. And you have now the very nice resonance, so no background at all, but for the breakup of helium-4. So that is what is called helium-4 continuum. That was what Dean was also referring to. And then there is the unknown form of the resonance. That's the blue N, which I had it since the beginning. So, and here Simon's approach was really systematic in that he said, well, I can I can use two different models for this background of the helium-4 continuum, and I can also use two different models for how this resonance looks like. The two model he used for the background was a linear background. You see it here in red. So assuming that the resonance is sitting just on a linear background, or just taking, as it's often the case, a Gaussian tail, so the resonance sitting on a Gaussian. And then you have the first part. And then to simulate how the resonance looks like, he used two line profile. One is the superposition of a Gaussian and a Breit-Wigner. That is something which is often used in physics generally. The other one is characteristic more for resonances near breakup, and that was first used by Jackson. So now you know where the resonance is, so it's 20 MeV, and you can just adjust gamma, so the width to the data, and here, and you combine two models for the background, two models for the resonance, and you get 4 different values for the width of your resonance, and they nicely agree with one another, and they also agree with what was present in the literature. But now the nice thing is that since you have all these 4 different combinations, you can determine a model confidence band, because that's something you don't know and you don't measure. You just assume with these background model and resonance model, and that is here in blue, and that is what in the table which we have published is written down under model uncertainty. So that gives us the largest value or the order of magnitude of our systematic error. To test the robustness of our method, we perform the analysis with 2 spectrometers, so A and B, and they both agree with one another, the data. So we are pretty confident that's the best we can do. Not yet, we could do a bit better, but I would love that you ask that during the Q&A question. And for now I do, so I give the floor to Sonia, blaming now the theorists, because even with this very precise data, they still don't fit with one another. So Sonia.
Yes. Okay. Share and play. No, wait a second. I want to do play rehearse slideshow. Okay. So it is my turn to discuss the theory. And let me start by stating that helium-4 is a classical few body problem for nuclear physics. We have 4 nucleons interacting with each other, which we want to solve from the quantum mechanical point of view, basically looking at the Schrödinger equation, where in this Hamiltonian, besides the kinetic energy, we will typically have a nucleon-nucleon force and a 3-nucleon force. And given these dynamical ingredients, we aim at obtaining a numerically exact solution, and there are various ways to do that, which typically agree in reproducing the ground state energy of the alpha particle. However, what we are targeting here is the transition form factor from the ground state to this 0+ state, which, as Dean already said, is a resonance situated above the proton emission threshold and below the neutron emission threshold. And while it is a resonance, it is relatively narrow. One could approximate it as a bound state, but rigorously speaking, one should deal with it with a method that can treat the continuum. So before the paper by Kegel et al., the situation could be summarized by these 2 extreme calculations. The first one by Yama et al. In 2004, where the Gaussian expansion method was used, a very well-established bound state technique, with a simplified 3-nucleon force, which is purely central. And that led to this black curve that went very well through the old data that suffered from large error bars. And then in 2013, we did the calculation with a state-of-the-art chiral effective field theory potential, using as a solver a different method, which is the Lorentz integral transform with hyperspherical harmonics. And we obtained this high result that Concertina already mentioned. Let me say a few words about the ingredients we used. So why I cannot move on? Yeah. So first of all, the chiral effective field theory is a way to derive nuclear forces, starting by effective degrees of freedom, the nucleons and the pions, but preserving the symmetries of the fundamental QCD theory, in particular the chiral symmetry. And this leads to a series of diagrams that characterize the nucleon-nucleon and 3-nucleon force, which can be organized in order of importance. And here you see the diagrams that were considered in the calculation that we did. In terms of the solver, numerical solver, we used the Lorentz integral transform, which is a method devised to deal with response functions in the continuum. Response functions normally, generally, can depend on momentum transfer and on energy transfer. from the electron to the nucleus. And if we look at the monopole, we can have a contribution of this response function due to this 0+ first resonance, but there can be a background, exactly as Concetina said in the experiment, there can be a background also in the theory. This time it is generated by higher energy monopole states. So if you imagine that you are able to isolate the resonant part and you integrate around the energy region, you get something that then is a function of Q only, and that's the form factor. So what we did in the theory, we worked on a fixed Q grid so that the response function at each Q is depending only on omega. We apply an integral transformation to obtain the norm square of a state psi tilde, which is found as unique solution of this Schrödinger-like equation, where M here is the monopole operator. And we solve this bound state equation with hyperspheric harmonics, another well-established few-body method. What we do see is that for the monopole resonance, we see one pronounced peak, which is located not in the right position, is a bit too high. And then we see a bunch of other states that constitute the high energy monopole background, which we can very well subtract by inverting this transform and getting the response function with the continuum. So we remove this little piece here. That's a drawing, but that's to give an idea. Okay, and that's how we got this two large result. Now, what did we do from the theory side in the Kegel paper? So we did a new calculation in the sense of a benchmark, which is something that in few body physics we do a lot. So there were these main two results that were obtained with two different methods and two different potentials. So we then decided to use the very same potential used by Hiyama et al., this simplified three-nucleon force, and perform the calculation with our different solver, namely the Lorentz general transform with hyperspheric harmonics. And we obtain perfect agreement, which is shown in this figure here. That is the form factor divided by Q square, zoomed in into the low energy part. There are many curves, but I would like you to look at the dashed black one, which is Hiyama calculation. And our result with the very same potential is this gray band. So we have perfect agreement. We can also go through the data. However, the results with the chiral forces is too high, and so it is the result with another phenomenological potential, AV18 plus Urbana 9. So we concluded that the problem is not in the solver, but it's maybe in the Hamiltonian, and we left it with a question mark to be discussed. Now, since the appearance of this paper, there have been a few more calculations that I would like to put in the context. First of all, on the day of the publication, there was a viewpoint by Eppelbaum that was already mentioned, where he points out the importance of getting the resonance in the right position. And we don't get it in the right position. And this is also known from studies by the PISA group, Viviani et al., from 2020, where they have investigated the position of the 0+ resonance with a variety of chiral forces. And what they observe is a large dependence of the Hamiltonian, which is consistent with what we find. And it doesn't correspond to the experiment. So to me, this is already a puzzle per se. Then other calculation appeared, for example, the one of Michel et al., where they used their few body method and neglecting three-nucleon forces, they managed to reproduce the Kegel precise data, which are here, by tuning the position of the resonance to be corresponding to the experimental one. And next, there was another calculation by Meissner and Mr. Chairman and collaborators, where the lattice effective field theory was used with a simplified force of SU4 kind. And also they go bang on the Kegel data. And their conclusion is that there is no puzzle to the nuclear force. Whether there is a puzzle or not might depend on the force. That's what I would like to point out. But there is another thing that we all need to check better, which is the question of how we deal with the state, bound state versus continuum. And this was pointed out by this other paper that also appeared after the Kegel publication by Kamimura, and because they pointed out that our benchmark is for bound states, and that's correct. So what we need to do next is to investigate the role of the continuum, and the PISA group is now starting to do that because they have a method that can do this. And this is just a preliminary result by Viviani et al. That was shown at the Few Body Conference earlier this year in Mainz, where using similar potentials to ours, they also get it high. However, I have to say that this is preliminary. There might be factors running around, so we don't know exactly where it will be. So stay tuned, because this for sure is going to be continued. Thank you very much.
Thank you very much, Sonia. Thank you very much, Constantina. Very nice presentations. There were some questions already, so if you have more questions, go ahead, put them into the chat or raise your hand. I will go in order. So there was a question from Yoshio Matsuki. I'm interested in the implications of the lower order terms in the power expansion. Could you explain how these terms were determined and their significance? Does your work consider any higher order or relativistic corrections in this context? This is probably for Sonia.
Yes, I guess so. So I guess the question is referring to the expansion of the potential. So we did a calculation, the calculation that you saw here, used a two-body force at high order next to next leading order, and a three-body force at one lower order. I guess the question hints to the fact that we should do a calculation at leading order and then one at next leading order and so on, and see what their effect is on the observable. And if that's the question, I totally agree. We would like to do it. We are trying to get funded for doing this research, because that's exactly one of the important things. These terms are typically constrained on the nucleon-nucleon scattering data. And then to the question of the relativity, I think there is a lot of relativity in the potential. I wonder if the question on relativity refers also to the operator or not. I guess maybe.
Yoshio, you wanted to comment?
Yeah. May I? Yes. I was thinking about the power expansion of the in the momentum transfer. Q squared, the functions of Q squared, developed in the power expansion. And then there should be the lower part terms in lower part and the higher power part. And then,
yes.
Yeah, this, I guess you are thinking about the lower terms in the power expansion, but there should be some higher power terms. And then there may be some relativistic terms to be multiplied by the Lorentz transfer.
So I'm not sure, are you referring to the low Q expansion that we presented on the form factor, or are you referring to
lower part is what you're doing, and then I think this, look, you think this is significant, and then there should be some. Do you consider to include some relativistic term using some Lorentz transformation for the Einstein's special relativity? So the idea is very simple. So this is my question.
No, right. So we haven't done that yet, but I don't think at this momentum transfer it will be very strong effect. Especially, let's see, if I go to this, I think here you won't see anything. Perhaps at higher momentum transfer you can see something. But I mean, I don't expect that the relativity will solve this problem.
Okay, thank you. That's fine. Thank you very much.
Okay, thank you. There's a question. I think this is for Constantina from Yushashi. The question is, how could you assure that there is no background from carbon-12, which has an excited state at 20.5 MeV? Constantina,
yes, okay. I have read that, and since we have a nice plot of A1, I couldn't just stop myself to find it on some other slide. That's an example of how A1 can measure electron scattering on carbon. So you just do a very nice spectroscopy. And now what I've shown was this data, but I can also show it a bit more without too many lines. That is now what we measure in this empty. So in the target, you have helium. And if you take out helium, then you have whatever it's left over. You are right, that might be carbon. So what we measure is in red now. And you see all the different peaks. And now you simulate just aluminum, no carbon. And it just sits on the top of the spectrum. And to look at very At higher energies, that was what I was showing you. If there was carbon in that, we would have seen that, just because the resolution of the spectrometers is such that we could have even seen all the different resonances. So I hope that that answered the question.
Okay. Thank you, Konstantina. There's a question from Moshe Guy. He asks, can you measure the protons in coincidence? Helium-4, E, E prime plus P. Would that reduce the background?
Yes, but that reduces also the count rate. So the problem is that, of course, the more we say, the more exclusive you go, the lower the background will be, but at a certain point, your count rate goes really down. So we have some ideas to do that, but that's a very tough experiment, not because of measuring the protons, just because the coincidence just killed the count rate then.
Okay, thanks, Konstantina. There's a question from, let's see, from Maiterei Shah. Is the ground state energy of the helium atom related to the energy of the alpha particle? If yes, how? So maybe I can comment on that. So we're talking about nuclear energies. So the helium atom, probably you're talking about the binding energy of the electron. That's not directly related to the nuclear binding energies. Okay. Are there other questions? If there are other questions, go ahead and write them into the chat or raise your hand. There's a question from Jonathan. Could you point me to relevant papers to define the physical forces in terms of pairs? Do we I guess pairs of particles, do we need to add multi-body terms?
So we can point to papers. There are a lot of reviews, right, on the subject. And the McLeod, Meissner, Applebaum and company, there are various reviews. And yes, we need multi-body terms. In fact, we included the three-body force. The three-body force is necessary to get the binding energy correct. It doesn't make a large effect on this calculation, at least in our the force we used, and I can show that maybe here. So in the 2013 paper now, not in Skegel one, but we tried to remove the trinucleon force, and the curve moves. Now I have different colors, sorry for that, but the result with trinucleon force is the pink one, and the result without trinucleon force is the cyan one. So I would say the effect is much stronger on the binding energy, but this is for one specific force with one specific cutoff. It could be different if you try to use a different force.
Okay, very good. All right, there is a question from Yu Shasi, who asks, if you do in coincidence with proton, how long would you need to take the data?
So we have a program with helium-3, and in the audience there is Søren Schlimmer, who is the main driver of this. So if Søren wants to answer, we have some calculation on helium-3, but not helium-4, and so.
Yeah, so we have calculations on helium-3. On the other hand, you may know that helium-3 is extremely expensive, right? So this will be really a final boss for our measurements there. And calculations are so that within some hours or so, you can get really a significant statistics in all of these investigations. And what we really plan to do is to study different aspects of these three nucleon forces or even meson exchange currents. So using traditional potentials, it has been calculated that we should have really a good sensitivity there in this case on helium-3. So helium-4 has not been calculated so far, but I mean, from the experimental point of view, this would be the first step here to do this. So it is challenging, of course, more than just doing a single arm experiment, but actually it is feasible. Yeah. for some of those quantities which you want to measure.
Thank you very much, Soren. There is a two-part question from Vitek Nazarevich. I will read the first part, then we'll take the second one afterwards. The 0+ excited state is not a narrow resonance. It is a state sandwiched between two thresholds. Its spectral function has a shape that significantly differs from Bright-Wigner. What is the very meaning of the width in this case?
Should I answer from the, I don't know if Vitek
Sure.
wants an experimental question or a theoretical answer or a theoretical answer. So my all experimental answer is the width is just one of the two parameters you use to reproduce your resonance, so that you are sure that you are just counting this blue N, which I had. You're just counting the number of events underneath the peak. So it doesn't, and that was the reason why we didn't make a big discussion out of these width, as if we had measured the width of the resonance. It's just one of the two parameters which we use to reproduce that. That's the answer to my experimental answer to Vitek. So
yeah, this is a great answer, Konstantina. I just wanted to say that this is not your normal, usual resonance.
No, sure, it's not. We are not doing gamma spectroscopy, so it's not just a width.
No, it's a broad threshold state.
Yeah.
Okay, so Vitek, since you're on right now, you can ask the second part of your question.
So my second question is that in the paper by Michel, which Sonia mentioned, it has been demonstrated that this unbound state, which is in between actually three thresholds, right? Proton threshold, neutron threshold, and deuteron threshold. You know, this state has a structure which is a superposition of three channels involving three different cluster states. So Sonia mentioned new continuum calculations, which are ongoing. So the question is, can those calculations consider this three-channel situation, which in our opinion explains the data?
Yeah, so it's basically a question on the calculation that Viviane et al. Are carrying on, right? So I think that, yeah, they have definitely the nucleon, the proton triton in there. Possibly also the other, I'm not 100% sure, but definitely we cannot do this with our method as of now. So I think that is the best method available if you want to use the same chiral forces. So I don't know, I don't think Michele is not here because he's doing rehabilitation.
But we also use chiral forces in our calculations, right?
Yes, but
so I would not say that this is the best method available, Sonia. I think that the methods which we use is ab initio method, which is very proper here.
Fine, I think, but the point is that you have neglected the three-body force, which, as in my case also, I didn't see a large effect. That's probably okay.
Yes.
I think if I remember correctly from talking to Michele, they see that depending on the range of the force, the effect can be larger. So we are not talking about exactly the same forces here, and I think more investigations are needed. And if you can vary the force, the cutoff, etc., that's also interesting. Of course, these states, this threshold that you are mentioning are going to be important, and that's what needs to be investigated with other methods as well. I think though that physics is correct, and maybe that's the reason why we get it too high. I don't know. We'll look at this. Also, in my opinion, I think we really need to look at what's the uncertainty in the chiral calculation, doing an order by order expansion, because it might be larger than we anticipated.
Okay, thank you very much, Sonia. Thank you, Vitek. There's a question from Wim Dikhoff, who's asking, helium-4 E prime P hydrogen-3 has been measured. I think he's talking more generally. So does theory reproduce this result? So is there general agreement, I guess, theory with this?
Yes, this is again for me. I
Either
think
one. Yeah.
I think there have been calculations of this reaction with semi-realistic potentials that were kind of reproducing the experiment more or less. It has not been done yet for the chiral effective field theory potentials, as far as I know, unless maybe the PISA group has done something at very low Q. So it could be. I mean, I think it's, again, space for more calculations, because it could be like before that you do with a simple potential and it goes through the data, and then with a high sophisticated potential, something is changing.
So let me briefly comment on this. I mean, the excitation operator is dominantly one body.
Yes.
So removing a proton and putting it higher up is one of the main ingredients in this transition. So if you know how to remove the proton from the helium-4 going to the triton ground state, it seems like an extra constraint for theory to reproduce.
Yeah, definitely is usually going to this exclusive calculation gives you a lot more constraint. That's true. Yeah, I agree. Thanks.
Okay, thanks very much, Sonia. Thank you, Vim. There's a question from Robert Gristo. Are there astrophysical implications of this resonance?
I think indirectly, yes. There is also, my field of study is neutron stars. So the point is that it's indirect, because as Sonia showed, so if these calculations, which have 3 body forces in that, do not reproduce that, then it means there is something different about 3 body forces which we don't know, and that would change then how the equation of state, for example, for nuclear matter is in the interior of neutron stars. It's always, so a neutron star is a big nucleus, so alpha is a small nucleus, but somehow the physics underneath should be the same, and that is what we are after.
Okay, thank you very much, Konstantina. Thank you, Robert. There's a question from Terry Bollinger, writes, your 2021 paper mentions the upcoming MESA facility as operating in the ideal energy regime for this. What is the current status of MESA?
So, and for that, I would also give the word to Soren again, because he's the spokesperson of the small spectrometers, which will measure that. So he is updated on everything which is happening nowadays.
Yeah, and in fact, as you can see in this figure, the spectrometers have just been delivered 2 weeks ago, so there is good progress at the moment. And so the halls have not been given over to us completely at the moment, but still we can start to set up this whole experiment, all the experiments, and also the accelerator, of course. And so the idea, the plan, actually the schedule is that in about 1 year or so, we will have first beam just from the accelerator point of view, and then in first quarter of 25, slowly ramp up with the experiments. I mean, of course, first you will start to calibrate detectors and do alignment of your system and so on, but we are on a good track actually to get this done. Here and there are some complications, of course, but after year-long of planning and designing and all of this now really comes to a reality, and this is a very special, nice time at the moment. So basically, I think in 1.5 years or so, we will really start to perform kind of experiments. So starting with easy ones, of course, we will not do any proton form factor measurement on day 1 or so, but then we will better and better understand the machine, the detectors, and so on. And then we have a great program actually for 3 different experiments there set up. Yeah, so this is on good track.
Thank you very much, Søren. And thank you, Terry, for the question. There's a question from Longji Chen. who's asking about the nuts and bolts of the actual calculation. So this is for Sonia. How do you treat the master integrals appearing in the loop calculations, especially for the nth low contributions?
I will answer in a funny way. I let other people deliver me matrix elements so that I can do the nuclear structure part. So that's, of course, it's very tricky, but there are people who are specializing in devising the potentials and other people who specialize in using them. Ideally would like to do both, but it's not always possible.
Mm-hmm.
I mean, Dean, feel free to comment because you're doing both, so maybe you want to say something.
Yes, so a lot of the calculations are not done by iterating diagrams and doing loop calculations, but they're using some sort of a basis, and they do a fully non-perturbative calculation where you sum up all the contributions with a truncated basis. So that's the sense in which a lot of these calculations are done. Okay, there's a comment from Vitek. By the way, congratulations on outstanding experimental data.
Thank you on behalf of the whole A1 collaboration. Thank you very much.
Okay, and Terry says, exciting MESA status, thank you. And Langji also says, thanks a lot. Are there other questions? We have maybe about a few more minutes that we can go with this discussion.
There's no question. I have a question.
Sure.
I think on the experimental part, you are planning to improve the superconductivity, right? To increase the effectiveness for the detector. How do you, this part, would you think that this part can solve the puzzle, the discrepancy between the theory, the numeric simulation and the observation detected experimental data? What would you think? Are you not involved in the improvement of the detector by superconductivity? No.
I think it's more about a question of energy, but I let Søren answer again. We had prepared these 2 slides for the future. So Søren.
Yeah, I'm not sure if I understood correctly. So superconducting will be the cavities which we use, right? And the special thing about MESA, if you can go to this slide here, just behind this figure, is that this will have an energy recovery mode. And this will mean that, okay, you go through these cavities multiple times, and each time the electrons get 25 MeV energy. And then you have this ERL arc where this magic experiment will be sitting, and then you bring back the main beam to these superconducting cavities again, but with a phase shift of 180 degrees. And so this means that the electrons are not accelerated anymore, but they are decelerated. And they give back the energy to the system. And so you run multiple times through these cavities again. So all the electrons give back their energy to the system. And this now really provides a very energy efficient way of acceleration. And as a return, as a reward, you can achieve very high beam intensities. And this is the main clue here of this MESA accelerator, I would say. And in turn, this allows then that you can use a different type of target, actually. Maybe there is a figure on the left-hand side, yeah, for this magic experiment. And so we really don't want to struggle anymore with background coming from target foils and so on. But instead, what we will use is here such a gas jet target, which provides a very thin gas beam. So we do not have any foils, any background from this, and also energy straggling and multi-scattering inside of this target will be just negligible. And so this means that we can achieve a very high precision with our detectors, which are also optimized for low energies. And so the experimental conditions will be much better here, so that we can really improve in going down also to lower and lower momentum transfer regions here. And yeah, if this will solve any problem, I'm not sure, but at least we expect a very good data quality there in this case.
Thank you, Russ. So the improvement of the detector might be influential to the precision, not the solving, not for solving the problems, the discrepancies, the puzzle yet. May I understand like this? Precision is going to be improved much, but not
Yes.
that.
Uh,
That's it. Thank you.
Okay, there is one last question from Jonathan. Maybe I can comment on this. The question is, do I understand you're basically putting the two body force aside? Is it correct? As in the three body force is critical. Could the entanglement of two body forces be a potential alternative? So the two body force is the dominant contribution. There are three body forces, but they are sub-leading. They're not as important. There is definitely entanglement of the wave function. It's a very complicated thing, but when you write down the Hamiltonian, you have pieces. You can say there's a two-body term, a two-body force, there's a three-body force, and the wave function is completely entangled. It's a complicated object. All right, so this is, I think, the end of the discussion. So thank you, everybody, for participating.
Well, could I
Yeah.
substantiate that question slightly,
Sure.
if you don't mind?
Sure.
That three-body force that you're saying is so critical,
Mhm.
could that be an effect of entanglement of pairwise interactions of the four particles in the system?
Sure. For example, if there's another particle that mediates something that it looks like an effective three-body interaction, that can happen for sure. Like the delta.
Oh,
change.
like a meson or something, perhaps?
Something, yeah. You can produce such an effect. That's right.
I see. Thank you.
Okay, good. So at this point, I'm going to hand it back to Kevin. Go ahead, Kevin.
Great. I just want to take a second to thank everyone for attending. It was a great discussion. I learned a lot. A wonderful experiment and theory follow-up. So thank you all for your participation. And I just want to point out that the Journal Club is an ongoing activity, and they typically happen about once a month. It spans all fields of physics, so please check back. I think the best place is our website. You can find information on the Journal Clubs. They're posted there or on social media. And you should expect one sometime late next month. So with that, thank you again for attending, and I hope to see everyone soon.
Thank you. Bye.
Thank you very much. Bye.